In this lesson, we're going to look at graphs of polynomials, and first we're going to talk about the possible number of roots and relative max, mins, and specifically turning points, because most of your problems in this section ask about how many potential maximum amount of turning points you can have for each problem. Well, let's first talk about even degree polynomials. Even degree polynomials would be something like x to the second power is the highest power, or maybe they might have x to the fourth power or x to the sixth, anything like that. That's an even degree polynomial. An odd degree polynomial would be something like x to the fifth power as the highest, or maybe x to the third, or just an x. Okay? These have different end behaviors. So let's first talk about that, and before we talk about everything else, let's talk about end behavior. First, of even degrees. Okay? Well, if it was x squared, what that means is there's a potential that it could touch the x-axis 2 times. If it was x to the fourth power, there's a potential it could touch the x-axis 4 times. So it's all about the x-axis, and this number up here tells you how many times it can touch it. So x to the fourth could look like a w, okay, something like that, where it touches 1, 2, 3, 4 times, okay? Or it could be a negative w. Okay, so it can touch up to 4 times. So if it can touch up to 4 times, well, we need to talk about turning points. Turning points are when it's going this one direction and then it turns. This is a turning point. So this is 1, 2, 3 turning points. Now notice it was x to the fourth and it had 3 turning points. That's 1 less than 4. Okay, let's keep that in the back of our mind. So now let's take it x squared. Well, we've seen x squared graphs. That's a parabola. It could look like that. So there's a maximum amount of 2 places it could cross. Again, it doesn't always touch at 2 places. It could touch like this. But at maximum, it could touch 2 times. So it could touch none or 1 or 2 times, okay, for a polynomial. Now, that's one way it could look, or it could look like this, okay? Now notice the end behavior for both the x to the fourth graph and x to the second power. Whichever direction it started coming from, it ends up going back in that direction. X to the fourth, it starts in this direction, it ends in that direction. Okay, that's the end behavior. Anyway, let's talk about the turning points here. Here, there's 1 turning point. Okay, so x squared had 1 turning point. That's 1 less than the second power. Okay, so the maximum amount of turning points is 1 less than the highest power. Okay, now from that, possible number of roots. Okay, the roots that I said, if it was 4, there's 4 possible roots. It doesn't mean it has 4. All the pictures I had did have 4, but it could be that they actually have 3 or just 2 or none. Okay, so it has up to the highest exponent of roots. And then relative max mins is the same amount as the turning points. So it's 1 less than the highest power. Okay, well now let's look at odd degrees. Okay, odd degree graphs have a different type of end behavior. Well, in x, we've seen a line before like this. This is just a line. Notice this time we started in one direction, finished in the opposite direction as far as going up and down is concerned. So this is x to the first power. Now notice first power, 1 x-intercept. There's no turning points here. That's because 1 minus 1 is 0. There's no turning points. Okay, so let's do x to the third. X to the third is going to look something more like this. Notice I have 3 points of intersection with the x-axis. I don't have to, it just has up to. I could draw another one that looks like this, where it only has 1 point of intersection, but it has up to potentially 3 intersection points because 3 is the highest exponent. So that's 3 roots. I said intersection points, 3 roots. Okay. Now in regards to turning points, it's 1 less than 3, so there's 1 turning point and a second turning point. Now it's not that they always have 2 turning points. I could draw an x to the third graph that looks like this, where it's got like a little bend in it, but it's not. We don't really call that a turning point, because turning point means it actually turns around in the other direction and then goes back up in that direction. Okay, so it's always 1 less than the exponent. So, to finish, we could look at x to the 5th power. An x to the 5th power graph would look something like this, where it goes 3 and then it needs 1 more. Now notice it's got 1, 2, 3, 4 turning points. Potentially, they don't all have this many, but it's got 5 potential points of intersection. Okay. Now these were all positive graphs that I drew for these odd degree functions. Let's look at the negatives. So a negative x to the 5th would just be going like this. Okay. This would be a negative x to the 5th graph. Okay. A negative x graph would be just going down, and a negative x to the 3rd would be going like this down over here. Okay, so this would be negative x to the 3rd. So positive graphs that are odd degrees start from the left down here and go up to the right. They all did that. Negative start from the top left and end up at the bottom right. Okay, that's how negative odd powers go. Now going back to the even functions, the even functions all started with, if it's a positive x squared, we'd have a happy graph. If it was negative x to the 4th, we'd have a sad graph. Okay, so it doesn't matter what power it is. If it's even, they both start at the top if they're happy or positive, and they both start at the bottom if it's negative. Okay, so a lot of background knowledge to prepare us to graph polynomials. Well, it's all about the roots, which means that if this was my polynomial that's in factored form, I need to find its roots. We find roots by setting it equal to 0 and setting each one of these equal to 0. X equals 0, 16 minus 2x equals 0, and then 12 minus 2x equals 0. And we try to find all the potential roots. So I have one of them as 0, so that means this graph will cross at 0, x equals 0. Then I solve the second one. I get negative 2x equals negative 16, which means that x equals positive 8. Okay, so I put a dot over here at 8, so that's my second root. And then finally I get negative 2x equals negative 12, which means that x equals 6. Okay, so I have 3 roots. Now let's check it. I have 1, 2, 3 x's, which means if I was to actually multiply / FOIL this whole thing out, I would end up with an x to the 3rd power. Now I have 3 roots, x to the 3rd power. That's the maximum number of roots that I can have. And notice that I have a, if I look really closely, you'll see that I have a positive x times a negative x. So positive times negative, which would end up being a positive x to the 3rd graph. Well, positive x to the 3rd graphs start down in the bottom left and end up in the top right. Okay, which means I could connect this picture to look something like this. Okay, now that's not necessarily what it looks like. It could look more extreme. It could be something more like this. I don't really know, but I don't really care either, because having this picture in my mind is enough to pick the right graph in the lab. Okay, so that's all the information that I need to know in the graph. If you have your roots and you know where this graph starts and where it ends, you have plenty information on the lab to pick your correct answer. Okay, now if this was a negative in front right here, if this was a negative in front, then I would have just rearranged it and I would have started, let me erase a little bit. So again, if this was negative in front of my x to the 3rd power, that means that my graph would have looked like this instead. Okay, so it does matter what that number in the front does, and what I was talking about on this last slide over here. Okay, so let's take a look at this second problem. So the first thing I want to do is find my roots. Okay, so set each one equal to 0. So x minus 2 equals 0, x plus 1 equals 0, and x plus 3 equals 0. Which means that I'll have roots at x equals 2, x equals negative 1, and x equals negative 3. So let's go ahead and plot dots there. So 2, negative 1, negative 3. Okay. Now we're going to check how many x's I have. 1, 2, 3. So now if I multiplied that out, I'd end up with an x to the 3rd. And if I check my signs, I'd have positive times positive times positive. So this is actually a positive x to the 3rd. So very similar to the last problem. I'm going to start down in this area and end up in this area. Okay, so we just need to connect our dots like this, and I want to pick the graph in the lab that looks very similar to that picture right there.